Greetings everyone. Welcome to the course on VLSI design. My name is Dr. Prashant Bachanna, working as Assistant Professor in the Department of Electronics and Communication Engineering at Institute of Aeronautical Engineering, Dundigal, Hyderabad. So before we begin our discussion to the course of VLSI design, so we'll see what is the semiconductor market size. So this figure shows the semiconductor market size from 2023 to 2023. So as you can see clearly from the on in the x-axis, these are the years from 2023. There's a prediction till 2033. So we're taking it from this source. So on the x-axis, this is the market size in the billion dollars. So as you can see in the 2023, the semiconductor market size is about $544.78 billion. So as you can see, as a number of years, there is a prediction till that in the year of 2024, it is $584.17 billion. So as you can see in this graph, as per the prediction, because of the boom in the artificial intelligence and machine learning, and because of the other sectors that you will see in the upcoming sections, so the semiconductor market size is about to be about $1,137.57 billion in the year of 2023. So there's a lot of scope to this VLSI industry. So the same thing what we have mentioned is that is the global semiconductor market size was valued at USD 544.78 billion in 2023 and is expected to reach around the USD $1,137 billion in the year of 2023. So poised to grow at a compound annual growth of about 7.64 during the forecast period from 2024 to the 2033. So this is about the semiconductor market size in the specific Asia, Asia region. So as you can see, from 2030, this is also there is also the present market size of the Asia for semiconductor market size is about $287.79 billion, and it is expected to be around $611.73 billion in the year by the year 2023. So there is a gradual increase of the semiconductor market from year to year. So what are the reasons for the semiconductor market growth? So we'll see some of the factors for which the semiconductor market size, the factors we'll see. So the extensive usage of the semiconductor usage worldwide has given the factor, that is like the applications in the applications of electronics, then industrial equipment, then automotive, networking, and communications and data processing is the major factor for the boost in the semiconductor market growth. So this is the one reason. Then the rapid growing AI, that is artificial intelligence, machine learning, IoT, and wireless communication devices spurring the semiconductor demand. This is the second reason. Then the rapid urbanization and the industrialization coupled with the government investment for the development of numerous smart cities is expected to foster the demand for the semiconductor across the globe. So this is the third reason for the semiconductor market growth. So these are some of the factors we've seen. Then the growing demand of the semiconductor in the industrial equipment and automotive sectors has significantly contributed to the increase in the consumption of the semiconductors. Then the growing popularity of the electrical vehicles, as you can see, the electrical vehicles are being manufactured worldwide. So this is also one of the reason for expected to be the growth for the semiconductor industry. So apart from this, you can see these semiconductor materials are used in almost all the electronics appliances and the equipments. So these are some of the factors for semiconductor growth. So there is one more this thing, the semiconductor market share by the application wise. So as you can see, in the government sector, the usage of the semiconductor is 5.2%. Then in the automotive it is about 11.3%. Then in the industries it is around 13.6%. Then in the consumer electronics, as you can see, like almost all consumer electronics devices are made with the help of these semiconductors only. Then the data processing sector is about 23.6%, and the networking and communication is about 29.2. So this is the semiconductor market share by the application wise. So this was about the market size and this thing. Now we'll see in this course will be the course is divided into the 5 modules. So before we begin our discussion, we'll see what are the contents of the 5 modules. So in the module 1, we'll be talking about the introduction to the MOSFET, that is the basics of the MOSFET. In the basics of the MOSFET, we learn what is a NIC, then the different types of the MOS transistor, that is metal oxide semiconductor. Then in the MOS, we'll be talking about the different types of metal oxide semiconductor, which is widely used in the VLSI industry. Then we'll talk about PMOS, NMOS is the types of the MOS transistors, that is PMOS, NMOS, CMOS, and BiCMOS. Then we'll see the fabrication flow, that is the flow of the fabrication, how an IC is manufactured. Then we'll see the basic electrical properties of the MOS. Then we'll talk in detail about the BiCMOS circuits. Then here we'll derive an equation for IDS versus VDS relationship in the saturation region and ohmic region. So apart from this, we'll see the pass transistor, then NMOS inverter, various pull-ups and pull-up regions. Then at the end, we'll talk about the CMOS inverter analysis and design. So this is about the model 1, that is the basics of the MOSFET. Then in the model 2 will be we shall be learning, that is MOS circuit designs and processes. Here we'll see the VLSI design flow. So what are the steps involved in an VLSI design? So starting from the specifications to the till fabrication. So that will be seeing, and here we'll be discussing about the stick diagrams, then physical design rules, then the CMOS design rules. Then then we'll be talking about the Euler's rule, and transistor layout diagrams we'll be discussing for NMOS and the CMOS. Then at the end, we'll be talking about the CMOS nanotechnology, then FinFET and the CNFET. So in the third model, we'll be talking about the basic circuit concepts and the gate level design. So this model is divided into the 2 sections. In the first section, we'll be talking about the sheet resistance and area capacitance layers, and in the second part of this, we'll be talking about the gate level design. Then in the module 4, we'll be talking about the subsystem design. So what are the subsystem design of for an VLSI this thing. So here we'll be talking about the data path subsystems. So here we'll be talking about the different these things called as like shifters, ripple carry adder, that is like 4-bit carry liquid adder and all. Then we'll be talking about the carry select adders here. Then Manchester carry chain. Then we'll be talking about the ALU, then the multipliers, then comparators, then detectors, synchronous and synchronous counters here. So all these things we'll be talking in the subsystem design, which are very important sections of this VLSI design. Then in the module 5, we'll be talking about the programmable logic devices and the CMOS testing. Once the IC is designed at the end, it will be tested for all the possibilities. So this testing plays a very important role. So here in this, we'll be talking about the PLA, that is programmable logic devices, are the devices which can be programmed like each and every time to update its specifications. So programmable logic devices are important. So here we'll be talking about PROM, then PLA, programmable logic array, then PAL, programmable array logic. So these are the different types of programmable logic devices which are used in the process of VLSI design, that is programmable logic arrays and PALs. Then we'll be talking about the FPGAs, that is field programmable gate arrays. Then CPLDs will be talking about the complex programmable devices, that is CPLDs. Then we'll be talking about the architecture of the FPGA routing and the procedure. Then after that, we'll see some of the trade-offs like area, time, and the delay. So, and at the end, we'll be talking about the CMOS testing. There's a technique called built-in self-test, and here we'll be discussing test pattern generators using linear feedback shift register, that is LFSR. So these are the content of the course. That is, the course is divided into the 5 modules. So what are the objectives of the course? The aspects of the hierarchy VLSI design from the metal oxide semiconductor up to the system level of fabrication and the testing. the subsystem incorporating into a VLSI chip with the contemporary techniques for achieving the high speed, lower power, and low area. So these are the three parameters of designing an any IC. It should have area, power, and the size. Size should be less, area and the power. So these are the three important factors of the VLSI design. Then the advanced modern tools such as Vivado, Cadence, these topics at the end of the course, the students shall be learning. Objectives. So these are the outcomes of the course. That is the first outcome is summarize the MOSFET fabrication process, then electrical properties, scaling of understanding the latest development in VLSI. Then the second objective of the course is to use the stick diagrams, that is make use of the stick diagrams and layout designs to convey layer information in the MOSFET circuits. Then the third objective is analyze inverters, complex gates, and dynamic CMOS circuits to calculate power consumption, distortion, and the speed of operation. Then the fourth operation is illustration of data per subsystems and array systems using the stick diagrams and the layouts. And then the fifth objective of the course is outline the role of programmable logic devices for realization of complex Boolean functions. And the sixth objective of the course is examine the test strategies, implementation approach to fulfill custom design, and that is the speed, area, and the cost parameters. So we'll see the introduction to the VLSI. So VLSI stands for very large scale integration. So basically in VLSI, millions of transistors are implemented on single IC. So the VLSI term is divided into it is abbreviated as very large scale integration or integration circuit. So basically in VLSI, it is an IC. So before we begin our discussion, we'll see what is an IC. So an integrated circuit is basically made up of by using active components and passive components. So active components like transistors, SCR, and MOSFET, and passive components like capacitors, inductor, and the resistors. So an IC. So in the VLSI, what is very large scale integration? So in the VLSI will be basically integrating millions of transistors on single IC. So an IC is made up of these active and passive components. Now the question comes, so what are active components? So active components are the components which require electric power for their operation to turn on and off. So the transistor, SCR, and MOSFETs require the electrical power for their operation, whereas passive components like capacitor, inductors, and resistors does not require the power supply. So that is the difference between the active components and the passive components, and an integrated circuit is made up of these combination of active and passive components. Then we'll see the evaluation of ICs. That is the evaluation of IC has started from small scale integration. At the time on the single IC, up to 10 to 100 transistors were implemented. That is called as small scale integration. Then after that, medium scale integration, wherein on single IC up to 100 to 1000 transistors were implemented. So this is how the evaluation has started. Then in the large scale integration, from 1000 to the 10,000 transistors were implemented on the single IC. That was called as LSI. And now in the VLSI, more than 1000 up to millions of transistors are implemented on the single IC. And because of this reason, the size of the devices has been reduced. So as you can see, in the year of 1970s and 80s, the size of the computers were equal to were very big, very equal to the room. So because of the integration technology, the sizes of the devices have reduced. As you can see, smartphones, palm tops, laptops, and all. So because of the integration technology, that is the number of devices implemented on a single IC has started from 10 to the millions now. So now on a single IC, we can implement up to millions of transistors. So that is called as very large scale integration. So all this evaluation of this thing has started from a very important law called as Moore's law. So Gordon Moore in the year of 1965 has proposed that so because of his prediction only, he has predicted at the time that the number of transistors on an affordable CPU would double every 18 months. So at the time, he has implemented for almost every 2 years or 18 months, the number of transistors will be doubled. So Moore transistor is more accurate according to the prediction of the Moore, and so because of his prediction, so as he has predicted at that time only, from 1965 to the till date, every year the number of transistors which were implemented on single IC has started doubling every 18 months, as you can see from here. So and now we can say it is in terms of the millions. So approximately every 2 years, personal computers and the electronic devices can do twice many new, innovative and unexpected things than before. So from the 1965 to the till date, the number of transistors which were implemented started doubling almost every 18 months or 2 years, and because of that, the sizes of the devices have been reduced, and these electronic devices have become innovative, and some unexpected good things have happened. So this graph shows the Moore's law. In the from the year of 1971 on the x-axis, there is like years have been mentioned from 1971 to 2016, and in the y-axis, number of transistors implemented. So in the beginning, we have taken 2003 from then 10 to the power 4, 5, 6, 7, and up to this thing. So as you can see, the Intel 404 chips which are developed in the year of 1965, then as the number of years increases, okay, so the different like 8088 processors and all, it was up to 10 to the power 5 transistors on the IC. So as you can see, from Intel 404 to the Intel 8086 and all these things, then and you can see at the end like Spark M7. So the number of transistors which can be implemented on the transistors have doubled every year from the year of 1970 to the till date. So as you can see, like every 2 years, the number of transistors in integrated circuits have doubled. So this is the proof for the Moore's law. He has predicted every 18 months the number of transistors can be doubled on a single IC. It can be implemented. So that is, we can see from 1977, the transistor technology was 10 micrometer technology, the size of the IC. So then now in the year of 2020, so we are into 5 nanometer and 3 nanometer technology now. So this is about the evaluation of the VLSI design as per the Moore's law. So again, this shows the Moore's law proof. One more example here, we are taken from the 1970 to the 2010 here, like 4004 here, up to like 100 to 1000 transistors were implemented in the IC of Intel 4004 IC, then 8008, then 808, then at the like in the year of around 1980s, the microprocessors have come into picture, that is 8086 ICs, wherein we can implement more. So every year, starting from this Intel 404 to every year, the number of transistors which are implemented have doubled. Now you can see from the graph. As you can see, like one more graph here from the year of 1971. So the number of transistors which were implemented on the IC have been doubled. So because of that, like in the year of 2010, like CU interconnects were used. Then in the year of 2010, then high K gate transistors were used. Then FinFET came into the picture. Then in the year of 2033, we are using 3, 5 and a GE channel. So because of which, as you can see, the number of transistors are doubling every year. So these are some of the references what we have referred. That is the Bucknell the author Bucknell from the basic VLSI design. So these are a few of the references we have used for the preparation of this video lecture. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.